Hi, here's the guided worksheet for week 4, section 2.1 on basic functions and their graphs. Let's go over the definition of a function. So a function is a rule of correspondence such that each element of a set D, called the domain, corresponds to exactly one element of a set R called the range. Important point is each element of the domain corresponds to exactly one set of the range. All right, let's take a look at the following diagrams to determine which ones represent a function. All right, well, let's see the difference between A, right, where we see actually each element of set X, right, it goes to one element of set Y. That works out. So that's a function. B is also a function. You might not think it is. Notice that just each element here goes to one Y value. It's okay that they go to the same Y value. The fact is that it's not like part C, problem C, where we've got one element of the domain going to two different elements in Y. So one X can't go to two different Ys. All right, but I can have different X's going to the same Y. There's a problem with D because this point, this in the domain doesn't go anywhere, right? So that fails. And then this is also part E, an example of a function, because every element in X goes to just exactly one element in Y. All right. Now let's take a look at this problem in a different way. We've got a set of points. We've got X's and Y's. The X's are the domain, the Y are the ranges. If I write like a mapping of each X where it goes to with the Y's, we can see that this is a function, right? Each different X value goes to exactly one Y value. In B, we've got a problem if we do the same thing, because notice in the ordered pairs, I have 1 listed for the X value twice, and it's going to two different Y values. So here's the issue why it's not a function. All right, we can also look at this in terms of just equations. Okay, so an easy way to kind of determine whether an equation is a function is to solve for Y. Notice here when I solve for Y, if I take any value for X and I plug it in, I only get one Y value out. That makes sense. So we see this is the function, this equation is a line. So for lines, they're considered to be functions. Take a look at B. When I solve for Y, remember if I take the square root of both sides, I have to do plus or minus. So the problem is if I put a value in for X, like let's just say 1 for example, I'll get 25 minus 1 squared, which is 1, so I get square root of 24. The problem is that it's plus or minus, right? So I actually get two different Y values out just when we input one X value. So that would not be a function. That doesn't happen with cubic functions or cube roots, right? So if I put in an X and I only will get one Y out. Similarly for absolute value. Now you might not think this is a function, but it is, because remember if I put a 5 in for X, okay, then I will get absolute value of 5 is 5 minus 2 is 3. I get one Y value. If I put a negative 5 in here, yes, I still get 3 for Y, but that's okay because we have two different X values going to the same Y value. That's okay, it's still a function. A visual way to determine whether a graph is a function is by the vertical line test. So the vertical line test says if a vertical line crosses a graph more than once at any value of X, then the graph is not the graph of a function. All right, in problem 4, let's pick out the graphs that are not functions pretty easily, right? Here's an issue here. The vertical line, for this X value, whatever it may be, I will have a Y, two different Y values that correspond to that X value. Here we can see we've got 1, 2, 3, 4, 5, 6 different Y values that correspond to whatever X value. So these are both not functions. In A, it is a function. For any X value here, we go and intersect the graph, it only intersects in one place. C is also true. The only issue we have here is around this jump in the graph. But you notice for this X value, it's only defined to be where the dot is closed. So x only goes to 1y, so it also is a function. All right, function notation, the way we write it is f of x. The f just names it, so I can call it any variable, q, r, y, whatever. I could have called it a name like Fred or Ginger. And then x tells us the variable. Again, that might change. If we're talking about something with respect to time, the x would become a t. So the x is the input or the domain value, and then f of x always represents the y's, and that's the output or the range value. The one thing that you need to know how to do is to just input, or I should say evaluate functions at different values. For a and b, it's pretty straightforward. You're just plugging in for x the value that you see. Just be careful here for b, because this is a common mistake students make. -7 squared is positive 49. It's not negative 49. Now, if we're dealing in parts C and D with variables, make sure you square both of these terms. So this would be 5 squared and a squared. You'd get 25a squared. You're going to multiply by the 2, and then this will be your final answer. We can't really simplify that anymore. For D, again, now we've got two terms, but we're really replacing the x by this entire expression. So it has to be a minus 4 squared minus a minus 4 plus 3. Here, don't get tempted to just write a squared plus 16. Don't forget the middle terms. You have to write this twice and FOIL it out. Then that simplifies to this expression down here. Okay, another problem that you have to be able to do is if I just give you a graph, you want to work backwards. So if I start at -3, I want to find the value of the function. Well, I have to either go up or down to wherever the function is. Here I would go up, right? And then the value f of -3 would be positive 3. Here, if I'm at 1, I can't go up. There is no graph up there, so I have to go down to where it intersects the function and then over to the y-axis, and that turns out to be -5. Remember, the zeros of the function, we're looking for, the x values of the x coordinates. So the zeros would be here approximately, again, just estimating -2.5 and 2.5. And the y-intercept is where the function crosses the y-axis, and it would be at 0, -6. The domain and range of a function is quite important. So the domain is the set of all x values for which the function is defined, and the range is a set of all y values that the function takes on based on those x values. One way to determine this is to just draw some, maybe with different colors, the sets that might represent the domain and the range. So here's our function. What we want to do is we want to project these y values down to the x-axis. So here we would project up, here we project down, and that's going to give us the interval that represents the domain. So this round brackets or square brackets matter. So in this case, since there's a closed dot, that means that -3 is defined for the function, where here, since it's an open circle, the x value of 5 is not defined. So our domain would go from -3 to 5. Now, what we want to do is to find the range values. You have to now go to the y-axis from either kind of end of the graph. So this would go to -4, this would go to 1. So notice, because there's a closed dot, we'd include -4, and there's an open dot, we wouldn't include 1. So that's the range. Similarly, this graph, it stopped, right? There was a closed dot and an open dot. Here, it's an absolute value function, but it keeps going. So if this graph kept going and I went down to the x-axis, this would just keep going further and further to the left. Here, as the graph went out, this would keep going further and further to the right. So we see the domain is all real numbers. All right. In this case now, if we're trying to figure out the range, well, notice it starts at -3 and then it goes up to positive infinity, right? So you see this graph, if I were to go over, to the y-axis, it would just keep going up further and further. So this is -3 including that point, and then comma infinity. This should be a round bracket. Sorry, I omitted that accidentally. C is kind of similar to A, right? Because we have these, it's actually like a function that's on this closed interval. So if I go down to find the domain, go down to the x-axis, it's at -5, and this is 3. Since these are closed dots, my domain is -5 to 3. Now we have to see the y values. So you have to look at the minimum part and the maximum part in a way. So here this minimum is at -2, and then at this endpoint the highest value we see is at +2. Because these are closed dots, right, there's no open circles here, then our range would be -2 to 2. Try a few more of these. I put a GeoGebra app on our Canvas website, so you should try a few more of those, and I've talked you through a video with that as well. Now let's take a look at some graphing of functions. Here you can just plot some points. These are both graphs of lines, and you can create a table feature in your calculator. You know how to do that. These are the graphs you should get. What you want to do is just describe what's happening. This is going to lead us into transformations a little bit later. Notice what's happening for every point on the graph y1 equals 2x. y2 equals 2x minus 3 is shifted down. So I could take this point and I'm shifting it down 3 units, this point shifting it down 3 units, every point that occurs. And that's what this -3 means. It's taking the graph of 2x and shifting it down 3 units. One last problem we want to take a look at is an application problem now based on this, on functions. So it says a chemist working on a flu vaccine needs to mix a 10% sodium iodine solution with a 60% sodium iodine solution to obtain a 50 milliliter mixture. Write the amount of sodium iodine in the mixture given by S as a function of the number of milliliters of the 10% solution used, which is given by X. This was S and this is X. So we want X to be the milliliters of the 10% solution. That means if I have 50 milliliters to start off with, I'm taking X amount out for the 10% solution. That means 50 minus X has to be the milliliters of the 60% solution. So my function that gives the amount of sodium iodine in the mixture is going to be 0.10 times X, okay, plus 0.60 times 50 minus X. So we have X milliliters of the 10% solution, and then the remaining, which is 50 minus X, milliliters of the 60% solution. That is the function. So notice we're using function notation here on the left. Now we want to find and interpret S of 30. That means let X be equal to 30. When I do that, I get 15. That means that there are 15 milliliters of sodium iodine in the mixture when 30 milliliters of the 10% solution is used. Remember, X is the milliliters of the 10% solution. All right, that wraps up this guided worksheet, section 2.1.